Okay, we're ready for the second part of the afternoon session with Peter Schupp, who will speak about fuzzy light cones and deformed micro-causality in cosmology.
All right, thank you, Leonardo. Thank you, everybody, for coming. Thanks for the organizer for organizing it. It's great to see you all here again, so many people. All right, so I'm going to tell you about some work in progress done with Marvin Pinkford Walker and Marco David. Hello, Eugenia. It's work in progress, so it's going to be more qualitative than usual, fewer equations, more pictures and comments and remarks. Criticism is very welcome. Please interrupt me. So let's start with some introduction. What we were interested in was the horizon problem. We wanted to understand that maybe you can do without the horizon problem by just looking at some quantum geometric effects. And in the end, we actually convinced ourselves that generically you should not have a horizon problem, but let's see. Okay, some propaganda. We have two hugely successful theories. On the one side, general relativity for all the large distances. On the other side, quantum field theory, almost outrageously successful theories. They are not consistent with each other, but they describe almost everything that we see. If you want to see the largest structure of the universe, we use telescope or radio telescope and look out. If you want to see the smallest structures, use some accelerator. But if you want to see even further, even smaller distances or larger distances, we use mathematical structures to extrapolate. And I guess that's all. That's what all of you are doing here. You're inventing some structures to see even further. Actually, the two things, the small scale structures and the very short scale structures were connected. It's the quantum fluctuations at the beginning of the universe that spawn the structure formation in the universe. So it kind of fights itself into the tail. In cosmology, we have a very nice model that we also call the standard model, almost as successful as the standard model of particle physics. That very nicely describes things like the spectrum of the cosmic microwave background. Typically, at the beginning, you have a big bang, then maybe some inflation or not. Well, you got the dark ages, formation of galaxies, etc. So you all know these things. So that's the standard model of cosmology, but it also has some problems. Here, four famous ones. There's the horizon problem that we are interested in. There's the flatness problem. There's the monopole problem. And finally, there's a structure growth problem. So one could argue that the first three of them are really fine-tuning problems. You could set the initial conditions of the universe in a way so that you would not have these problems. Yes, Thomas? But there's too many monopoles generically. You would predict the production of many more monopoles than have been seen. So far, none have been seen. Magnetic monopoles, yes. Exactly. So there should not be so many, but there would be many if. So that's the problem. Exactly. So maybe we were just lucky and didn't get hit by one, but yes, that's the problem. But these are fine-tuning problems. The last one is a bit more serious. You would expect a kind of flat spectrum of structures, but predicted would be a different spectrum where you have much more structure with small scales than at larger scales. Okay, all these things are usually solved in quotes by inflation. So the idea is pretty simple. You have initial quantum fluctuations. You get a wild structure of your space-time. You zoom in on a little bit and you expand it exponentially using inflation, thereby flattening it out, getting rid of or postponing the horizon problem, making everything flat by exponential expansion, diluting the monopole so you don't have that problem anymore, and very nicely predicting the correct initial conditions for formation of structure in the universe. Okay, it's a nice picture. I call it naive inflation, so it's a great idea. But if you want to make it more quantitatively, it has theoretical problems. Maybe not so much prediction or post-diction problems, but theoretical problems of all kinds of things. Namely, with fine-tuning, even gets worse than before. So as you're expanding, entropy should go up. So you have to fine-tune the initial conditions of inflation even more precisely than you would have to fine-tune things up here. When it doesn't stop, it just keeps going in little spots. You get a creation of lots of multiverses. So you would have to invent something to make it stop. Some of the initial inventors of the whole theory, like Steinhardt and also Penrose, have went into opposition of this idea of inflation. Penrose even claiming by some estimate that reaching the present universe without inflation by just fine-tuning the initial conditions is 10 to the 10 to the 100 more likely than to get this thing out of inflation. Okay, I'm not going to say whether inflation is good or bad. We'll see. Okay, just a quick reminder about the horizon problem. Here's an observer today, looking back at the last scattering surface. That's the backward light cone. You compare with the forward light cones from the Big Bang. And when you notice that the time from the Big Bang to the LSS, there was not enough time to get all these regions into causal contact with each other. And so looking back, you would expect to see very different type of universes in these patches when you're looking back, unless everything was really nicely fine-tuned at the beginning. You can make that even more quantitative with a scale factor A of t going like t to the p in the FLRW model with p less than or equal to 2/3, like 1/2 for radiation, 2/3 for dust. You can estimate about 1,000 independent patches on the last scattering surface. Okay, when you actually look back, look at the CMB, you do see fluctuations. Here's a picture of fluctuations on the order of 10 to the -5 with the dipole excluded, yes? Yeah. Yes, yes. Yes, so there are many suggestions to resolve it. Inflation is one, bouncing universes are one, and there are more suggestions, yes. Okay, so when you look back, you see fluctuations on the order of 10 to the -5, but that's much, much, much less. It's almost a perfect black body. That's much less than you would expect if the horizon problem was really there. So our universe is near uniform, nearly flat distribution of matter with a nearly flat geometry. Okay, so our question was maybe there's no horizon problem to start with when you take quantum gravity and quantum geometry into consideration, with or without the use of inflation, which could come on top. But question is, maybe that's already enough. Well, let's see what was the problem with this horizon problem. What were the model assumptions? It's only general relativity was used here, and one assumes that one has a smooth space-time down to the shortest distance scales. So naively, when you look at the Big Bang, everything is flying apart. We extrapolate really naively back. It looks like everything came from a point. But these are just points that go closer and closer to each other, and on a smooth manifold, they never meet. So it's not really one point where everything talks to each other. In particular, it was assumed that quantum mechanical effects, except for the fluctuations, play no role here at all. In such a model, the universe simply cannot be in complete causal contact. Even with inflation, you're just postponing the problem into the future when you start seeing patches which were not in causal contact before. Yeah, but the world is quantum, as we know. And there should be quantum gravitational effects which were not taken into account here. That's obvious, right? Okay. Now, very naive way of looking at it. So we look at some observer at the last scattering surface or even earlier. We look at the light cones. And for radiation-dominated universe, we would go, for instance, like x squared. T goes like x squared, but that doesn't really play a role. The thing is, they go to 0 in a finite distance, but at a 0 slope here. Going back in time, t to t equals 0 to the Big Bang, you would expect quantum gravitational effects to play a role at the very beginning. So you shouldn't use just general relativity. You shouldn't use Riemannian geometry to describe the light cones back here. So a 0 slope. And another assumption, let's say we put Planck time ticks on the t-axis. We assume that they're equally spaced. If there was just a tiny little finite time uncertainty all the way down to t equals 0, when you couldn't tell anymore which light cone you're sitting on, could be on the next one. And if you extrapolate, actually the corresponding spatial uncertainty would be diverging would go to infinity. So everything would in fact be in causal contact in such a fuzzy type of light cone. Okay, very naive picture. Right. If you describe causality from a point of view of quantum field theory, you should look at commutators of quantum fields at different points. You can see when they are 0, things are not in causal contact. When we're non-zero, we are in causal contact. If we now have these blurry light cones, then we would expect to find operators at all spatial places initially, which are non-commuting. If you look at the evolution of such a universe, even if you start from a non-entangled initial state, you would expect the state to become entangled immediately because all your operators are non-commuting where they're acting on it. So from this very naive picture, you would expect a completely entangled, actually maximally entangled initial state of the universe and no horizon problem. Okay, but these are pictures and lots of words. And okay, some criticism here. You of course make lots of assumptions here. One of the things is a smooth continuation of light cones, kind of naively. We go back, we have 0 slope, you introduce another evolution parameter, and you just continue them flat. So that the finite time uncertainty will give you an infinite space uncertainty. Well, that looks a bit more reasonable in conformal coordinates. This would be the corresponding continuation. But even here, you should note that everything below the x-axis is the same conformal time, eta equal to 0. So you again have to introduce a new parameter. Furthermore, assume that somewhere close to t equals 0, quantum gravitation and quantum geometric effects kick in and blur the light cones. And there's some more technical stuff. I didn't tell you computations that were going on. Some technical stuff here to assume that the exponent p in the scale factor has to be less than 1. All right, so that was the idea. And when we tried to actually be a bit more predictive to get to compute quantum fluctuations, etc., in such models. Now, all of you, I guess, have worked on some kinds of non-commutative models. The simplest possible one that could actually already do the trick is with time uncertainty, uncertainty relation. So we want a non-zero delta t at t equal to 0. If you believe that in quantum mechanics this will still hold in that regime, if t goes to 0, then delta E would go to infinity, and that would again spoil all the predictions of cosmology. So we would have a huge energy density, probably lots of primordial black holes that you don't see. So even that already might do the trick. But we really would like to have a concrete model that tells us why delta t alone should be non-zero, or maybe why delta x should go to infinity. And the idea was to write down some non-commutative models, some concrete non-commutative models that would do the trick. The nice thing is there are very, very many non-commutative space-time models that exist, and all of you have, or most of you have, worked on these. Problem is, they should have the same symmetries as the FLRW space-time, and that makes it a bit harder. It's not so easy, so you want it to be isotropic. You want to have translation symmetry. Here are some favorite models here. It's like canonical quantization relations. These are obviously not isotropic. The theta will define 2 directions in space-time. Okay, when you could do a trick like Dopplischer, Fredenhagen, and Roberts and say, okay, this is really an operator. Should look at expectation values of it. Maybe it's varying throughout space-time. And then you can make some progress here. So I'm not ruling this out. I'm just pointing out that it doesn't obviously have the symmetries that you want. And would probably make some predictions that you could see or maybe should have seen already and maybe are not consistent with observations. The second example is isotropic, but it's not translation invariant. It has a preferred point. And the last one is a nice one. Part of the commutation relations, I guess, of Kappa-Minkowski space. So with this one, I would have the issue, but if you look at the uncertainty relation, it would go something like an expectation value of a position, and when it would grow too much, so I think that's an unnatural model. Why should the uncertainties grow when you're just further away from the thing that you look at? All right, so in summary, we do allow moderate Lorentz symmetry breaking because the FLRW metric is not Minkowski space, so that's fine. A preferred time is okay also, but we want it to be isotropic and translation invariant. So maybe somebody has a suggestion what we should take here. We didn't know exactly. Yes, just some examples that you get when you try to quantize space-time and look at light cones. It's a very old one by Bianca and Julius. You get some discrete structures. Here's stuff that I got in my own work. Again, some discrete structures, and there's an artist impression what you might expect. But this is not a fuzzy light cone like I would like to have it. It's more like a discrete space-time, so that wouldn't help much. There are also non-associative models. They might be a bit nicer because they're translation invariant and also isotropic. Here you have the commutators of the positions going into momentum, and this R, just think of it as epsilon ijk times some dimensionful quantity. This structure is not associative. You have an associator that goes like epsilon ijk, kind of an intriguing model. It has the right symmetries. It leads to volume discretization or quantization, so that's also nice. So in recent work with Richard Chava, we even found some kind of a GNS similar construction here, but we really don't know how to do quantum field theory on such a space. And then physical motivation is also not clear at all. So why should that have something to do with early universe cosmology? This is something that you would expect from some monopole background field. So physics is questionable. All right, so let's go back to the drawing board. We have general relativity, we have quantum field theory. In combination, we have some type of quantum gravity. In general relativity, you have this lambda CDM standard model of cosmology that gives you the horizon problem. It's a problem about causality. Causality in quantum field theory is described by the commentators of quantum operators, or micro-causality, and now ways to solve it. As already mentioned by Thomas, bouncing cosmologies, there are some variable speed of light ideas. There's definitely the inflation type of ideas. But how about on the right-hand side? Can we do something here to also solve the problem? And when the idea is, we don't want to make space-time non-commutative, but we want to deform the canonical commutation relations of the fields instead, make them non-local, because that would solve the problem. So how about non-local deformed CCRs for the quantum fields? Okay, that's the point where you say, okay, if you do that, then forget about quantum field theory, you can't do computations anymore, it will become terribly complicated. But surprisingly, this is not the case. So we looked at this model. We have the quantum fields here, conjugate momenta to them, having the ordinary equal time commutation relations. But we deform these, the delta function, we smear it, and we allow here a function that is not just localized at x equal to 0. Think of that function, for instance, just an example, think of it as being a Gaussian like this. I think everybody that started in this field might have had the idea to write something like this down in 1 minute, and in the second minute immediately thought, well, that's trivial, right? You can immediately get that by just smearing the fields. Just take local quantum fields, smear them with a Gaussian, compute the commutator, you get the Gaussian on the right-hand side. But that's ordinary quantum field theory, so it wouldn't solve anything. Okay, that's also what I thought. I think 20 years ago, first time, maybe 10 years ago again, and so on. But it's not true. You don't have to solve this by smearing quantum fields. You can think of these things still as localized fields, localized at a point, and really take it serious that you have a non-local commutation relation of the quantum fields, and that will give you a different theory, not a trivial one. All right, so think of this as being something isotropic, translation invariant, for example, a Gaussian. There's no physical motivation for it, just makes computation easier. So we take a Gaussian. Well, if you have heard talks of me before, you know that I like to deform commutation relations. It's a powerful tool to do all kinds of cute things. can use it to describe interactions, write down gravitational actions, and so on. Okay, like I claim, this is non-trivial if the fields are still considered to be localized, and it leads to fuzzy light cones. And it's a very simple model, and you can actually do computations in it, even though it's non-local. Well, obviously, it breaks Lorentz invariance, but it should. That's something what we're looking for. All right, so these are the new commutation relations. Fields and fields at equal time commute still. Momenta commute at equal times. You could, if you like, also deform your annihilation and creation operators, but then you could renormalize them and you just take the canonical ones. We just take the canonical ones like these. The normal ordered Hamiltonian then comes out in the ordinary way of computing things, comes out to have A dagger P AP as an ordinary quantum field theory. But instead of having here the energy corresponding to momentum P, which would be square root P squared plus M squared, you get in front the Fourier transformation of your smearing function. Yes? Yes, sigma has physical dimension. So think Planck length, or think something that might be time dependent, maybe some function of a scale parameter, A of t, something like this. Yes. Yes, of course, that's a deformation. That's something that defines the strength of deformation. If that becomes 0, you're back to ordinary quantum field theory, assuming that the limit is moved. Okay, so that's your normal ordered Hamiltonian. Now for a Gaussian, that becomes again a Gaussian. So for large momenta, this becomes really small. And so it suppresses the high energies. It naturally regularizes the expression. You get finite expressions when you usually get infinite expressions. So a nice model. The Heisenberg picture quantum fields, everything is canonical. There's not much you can do. There's no choices. You get out what you get out, and that's what you get. So it looks a lot like ordinary quantum, like a mode expansion of ordinary quantum fields, except in the places where you would expect the energy corresponding to momentum P, you get this regularized version of energy times the Fourier transform of the smearing function, and also the prefactors are slightly different. If you compute the field equations, you find that they're non-local. They involve like this pseudo-differential operator, where again you have the Fourier transformation of a smearing function sitting in here. So you've got non-local field equations. Okay, so we're interested in causality. We would like to compute the non-equal time commutator and figure out how the light cones look like. So this should usually be vanishing outside the light cones and be non-zero inside the light cones. It's one of the standard computations in quantum field theory. Well, nice thing is the computation is not very difficult. So here's the amplitude to have a particle created at place y and get annihilated at place x. Looks like the usual thing, except that you have an f of p instead of an e of p here, and you got a Gaussian in p squared in front. This will turn out to be in channel non-zero for x naught equal to y naught. So it will be non-zero outside the light cone. It's kind of obvious because at equal time already you have the non-local commutation relations, but it also holds at non-equal time. Another nice thing is that numerics are very simple in this model. So when you usually try to put such a computation on Mathematica or so, it will immediately tell you, okay, no, I don't do the integrals, you do it yourself. But in this case, it's nicely regularized, so you can, numerics is very easy, and here's what you get out. Here's the this dimension-full deformation parameter. It's just examples, maybe not very physical examples. Everything in Planck units here, 0.1 for the deformation parameter for a scalar field mass 1. So again, it doesn't make much sense, but just to get an idea, you get something that resembles a lot an ordinary light cone. So you get non-zero commutators inside the light cone and zero commutators outside. If you increase the deformation, then you get what we expect. You get this blurring of the light cones, and you can actually make this go all the way to infinity so that everything gets correlated.
The right one can be seen as the enlargement of the left one.
Not exact. Yeah, but there's a second.
sigma, when it's there, is actually the ratio between x and sigma.
But there's a second parameter, the mass of the field.
Okay.
So it will look qualitatively different. I've got a whole library of these pictures. So it's not just an enlargement of this one, no. So they become blurry, so a nice model seems to work. All right. Here's some computations, preliminary computations done by Marvin Pinkwart. Walker, yes? Down here, it's approximately 0. It's not actually 0, but they're very close to 0, as you can see. Yeah. Okay, so up to here, the ideas were let's not have a non-commutative model of space-time where we play around with coordinates and time and make them non-commutative, but let's again play around. Let's instead play around with quantum fields themselves and the commutation relations of the quantum field. And the second thing, a surprising thing, is that you get something non-trivial, and the third surprising thing is that you can actually do computations. All right, so here Marvin Pinkwart tried to find out what he can say about the fluctuation spectrum. He assumed a slightly de Sitter background and made some simplifying assumptions in the computation. So consider this as preliminary, but quite encouraging. Without deformation, you get a spectrum like this, which is not in agreement with the structure formation of the universe. In the deformed model, you get something that's more flat, not exactly flat like inflation, but nearly flat, and then drops down to 0 also at the shorter length scale. This is to be expected because the effects that we introduced, they play a role very close to the Big Bang, and we should affect these modes most. Okay, so preliminary shouldn't be taken too seriously, but it looks good. Some more effects. So it got a new quantum field theory, can play around with it. We do standard things. In the textbook, I guess on page 2 comes the Casimir effect. Take two plates at distance A, momenta are quantized like as usual. Compute the vacuum energy density, and here it comes out to be, as expected, to be finite because you got this natural regularization in it. So usually you would have this sum over n going from 0 to infinity, 1 plus 2 plus 3 plus 4 and so on. And when you set it equal to -1 over 12, you don't have to do this. You got an e to the minus n squared times some prefactors that render the expression finite. Marco David has done this computation. Compare that to the vacuum energy of the space without the two plates. That gives you delta E. You have this nice expression here. First term is that you get from the quantum field theory textbooks. The other terms are different. But in the end, the conclusion is that the Casimir force is the same as the undeformed theory, but you don't need to regularize because it's already finite. That's nice. Okay, when you think, okay, cosmological constant. If you think a bit more, it's clear that this cannot solve a problem, but one should look at it anyway. So let's compute the vacuum energy density. Well, it turns out to be finite, which is clear because you got a natural regularization in your problem, which turns out to be very easy to compute. It's 4 pi over this dimensionful deformation parameter to the 4th power. So that's nice. But then again, if you think a bit more about it, it can't solve a problem. If you think about the scales, and indeed, for reasonable values of a cosmological constant, that would require an unreasonable fuzziness of about 0.2 millimeters nowadays, or 50 picoseconds, which are both experimentally excluded, of course. Yes, then it wouldn't work. Yeah. Okay, so for this I should say that sigma should be of order of Planck scale at Planck time. I would expect it to have a different value later, but it's certainly, this is not compatible with experimental values. Yeah, but that was to expect, but one should do the computation anyway. All right, so this doesn't explain it. Additional other physics is still needed, but it nicely regularizes the number anyway. How about Feynman rules in this theory? It's non-local, so you would expect it to be quite difficult, but it's not. The only thing that gets changed is the Feynman propagator. It has this regularization through the Fourier transform of the smearing function. And down here, instead of having energy corresponding to momentum p, it has this regularized version of the energy corresponding to momentum p. All other Feynman rules are as before, and this is for scalar field theory, but you could also do it for other field theories. Marco David has done some computations here, some nice tree-level scattering, easily computed. Yeah, perfect. That's what he got out. So let's try to interpret what will happen here. So the scattering, the tree-level scattering, it has all these factors of the Fourier transform of the smearing function on top. So these are Gaussians in the momenta. This becomes small when the argument is large. So for large momenta, the scattering will be suppressed a lot, unless the momenta are aligned. If P1 is equal to K1, that will drop out, or if P1 is equal to minus P2, this will drop out. So if you have a momenta aligned, it will not be suppressed, but in all other cases, it will be suppressed. There's some more puzzles. I'm again not claiming that it solves them, but it seems to be relevant. There's this GC K-bound of 5 × 10⁻19 EVs of the highest possible energies in particles, in cosmic ray particles that you would expect, protons, from scattering with a cosmic microwave background. This may have many other explanations. Here, the scattering will be suppressed enough to explain some of the very high energy particles that were discovered. There's this oh my god particle, for instance. If the fuzziness today would be of the order of 6 × 10⁻28 meters. I can argue about this, but I think this is experimentally not excluded. Of course, that does not need to be physics of it, but okay, that's an interesting fact. Okay, so far so good and so easy. Well, in loop integrals, unfortunately, since the theory is frame dependent, some of the tricks, Feynman tricks that you cannot use anymore, it becomes very hard to compute these things analytically, or I would say almost impossible. But numerically, it's still very easy. You can compute with loop integrals. You find that everything is naturally finite because you've got this length scale in the problem. We can compute these things easily. All right, that's how far we got so far. It's work in progress. So let me summarize. In models like this, not only in this one that I presented, but in general, I would say generically you would not expect a horizon problem if you have a proper theory of quantum gravity that explains it away. In the examples, relatively conservative assumptions about the early universe will do to do away with it, or in the cases where our computations didn't apply, actually inflation will take care of it automatically. So one of the two will do it, or some bouncing universe. You would expect a fully entangled initial state of the universe if any of these ideas are correct. And regarding deformed micro-causality, this model that I showed you, I think it's nice, it's simple, it's effective, gives fuzzy light cones, you can do computations in it, gives natural regularization, and of course it breaks Lorentz invariance. If you want to read more about it, so far it's in Marvin Pinkward's PhD thesis and Marco David's bachelor thesis, and we're preparing publications on it. Thank you for listening.
There are quite a few questions. The first one I saw was Harold.
And I should say I apologize to the speakers this morning, which might have given talks which are relevant for this, but I was on the plane.
Okay, so I have one comment and one question. So the comment would be, I mean, relating to these non-commutative algebras you discussed in the beginning for cosmology, which should have these properties. So there is a very nice specific model which has exactly these properties. You know it, with Markus and myself. And the point is, it has exactly, so it's between time and space is the dominant non-commutativity, and space is almost commuting. So that's exactly what you seem to like.
Yes.
So that may be of.
I agree. So my list was a bit short.
Yeah. Okay. Anyway, and the question would be, so you change the canonical commutative relations in the end, but somehow when you try to give some non-perturbative definition of a model, you usually take a path integral, and then canonical ones just come from the Gaussians, which is totally natural. So you would have to change Gaussian terms in the path integral thing to something non-Gaussian, right?
Yeah, we're
would it
starting
be-
to thinking about whether there's a path integral description of it or not, but it's completely unclear to us because
Yeah.
it's non-local. But I'm not excluding that it's possible. Need some more thought. Maybe you have some ideas.
Yeah. Yeah. Anyway, it seems to be not clear how this would be natural, but okay.
I agree.
For the loop diagrams, do you expect something kind of like UVR mixing, meaning that when you remove, because I mean, typically it's quite dangerous business. I mean, really analytically to remove your regularization essentially and to see that everything is fine. I mean, so because numerically, typically you would not see that. I mean, so that's my point. I mean,
Yeah, okay, I know the problem. So we worked on it a long time ago in non-commutative gauge theories. I would not expect that here unless you come up with a model for sigma as a function of the scales which introduce it by hand. But other than that, it's just UV regularized. We didn't do anything with the infrared here. The sigma is irrelevant for the infrared.
Two questions. First, the theory that you are describing here, is it free of UV divergences at every level in the
So naively, I would
loop
say
structure?
yes, but we only looked at loops and at Casimir effect. But naively, I would say yes.
I don't
It's
know.
regularized naturally.
I don't know if I guess that because you mentioned it, there have been some works related to the duplicate Hagen-Roberts spacetime by like 5 or 7 years ago from Morcella duplicate and Pinamonti. They also claim that they solved the horizon problem and also have obtained a theory that is free of ultraviolet divergences. So I find quite similar these results.
I'm aware of that work, yeah. And I can give you references. So we got about 100 references. Lots of people have similar ideas, but not that model.
Thank you.
Short question. What is the spectrum of energy in these models? Is it bounded below?
The spectrum of energy.
Is it bounded below? Does it have a gap in the massive case? Whatever. This is a usual problem in different time.
Yes, I
Conjugated.
understand. Yeah,
What happens here?
I have to think about it. I cannot answer you. Yeah. Good question.
Question on the back.
So can you go back to this slide where you showed the spectrum, the graph? Yeah, so I just want to know what is the computation you did here?
What is the computation I did?
Yeah, so
So I didn't do any computation. This computation was done by Marvin Pinkwart-Walker, and he just mimicked the classical computation of the fluctuations as can be found in books by Mukhanov and others.
Yeah, but I'm exactly asking because of that. So you normally have to pick an initial state to do these computations.
Sorry?
You have to pick an initial state to do the computations. So what state did you choose?
Yeah. Okay. Can we discuss this later? Because I'm actually interested in it.
Sure.
Yeah, thank you. And I said it's preliminary. It's just don't believe it yet.
Hi, Peter. Have you checked whether there is any unitarity issue with this? Any unitarity issue?
Oh, because okay.
Minkowski's rule and all that.
Unitarity issues because of space-time non-commutativity.
No, not because of that. It is because if you apply Minkowski's rules, it's not clear to me that at one loop there is no unitarity issue with the.
That's true. That's a good point also. Yes, thank you. I have not checked, no.
Anyway, nice talk.
I should, or you should. Write them all down.
The calculations you showed us were for quantum field theory in flat Minkowski.
Yes, that's true.
Have you done it for FRW? Because there's something similar should work as well, right?
Yes, so that's concerning this thing. So it was first done in Minkowski spacetime and then, but not very rigorously, in slightly de Sitter spacetime. This has to be done more carefully.
One last question by Alexandra.
It was also Bencho, right?
Oh, there is some. Okay.
I think Grant Bencho one, right? Sure.
There is a paper by Dorothea Barnes, Sergio Doppler, and I think Fredenhagen and Piacitelli, if I remember correctly, where they, in their model, DFR model, they gave bounds, lower bounds on 2 volume, 3 volume, 4 volume. There must, and it is in their model, okay? But there must be some relation. Is there any relation of that approach to this one? There they claim they are not breaking lower.
Actually,
at all.
Actually, this is more related to with non-associative models. So I didn't write that down, how we get this volume quantization. That would be a different talk, but that's using structures exactly like the ones that they were looking at. So that's not related to the model that I showed you later, but it's related to this slide. And then show the question.
Yeah, if I understood you correctly, you've only affected the spatial part, so it's an expansion in higher derivatives, but convergent expansion. So you've got a Gaussian. I would expect that that running couplings will behave ever so slightly differently.
Sorry?
I would expect that running couplings will behave ever so slightly differently. I think your leading divergences are going to pick up the logarithmic divergences. You showed us the quadratic divergence in the tadpole diagram, but I think there'll be ever so slight changes to the running couplings, which might be interesting to look at.
That's also a very good point. I put it on the list, yes. And that also might disqualify the model or give something interesting, yes. Thank you.
Okay, seems that there are no more questions, then we can thank Peter again. And we proceed to the next talk by Markus Froeb on non-commutative coordinates from quantum gravity.
Yes, yes. That's the pointer.
20 plus 5 for questions.
Okay.
I give you a warning at 5 minutes.
Okay. Okay. Yeah. Thank you very much to the organizers for giving me the opportunity to present my results. We've heard many talks on starting from non-commutativity and then getting quantum gravity. And I think, well, why not turn this around? Let's start with a very conservative approach to quantum gravity, which is the perturbative approach, and see if we can get something non-commutative. And well, as you see from the title, the answer is yes. So I'll tell you a bit about perturbative quantum gravity. Then what one can actually measure in quantum gravity. This is something that everyone should think about. And I believe there's an answer. And then I'll tell you about what comes out of that, of thinking about these things. And I'll conclude, and I'll try to stay on time since it's late. Okay, perturbative quantum gravity. What do? We take gravity, and let's say take the Einstein-Hilbert action with some cosmological constant, very nice. Add some matter action, fix the background, very classical, and then do fluctuations around that background. So expand say the metric to the background metric, and perturbation h mu nu. And then, well, the first thing you do is you do linear approximation, and linear in that case means that you take the gravitational action to second order in the perturbation, because that gives you a free field, free graviton, and the matter action to linear order. And then people have been computing things in this approach for a long time. A very nice example, straightforward, are one-loop quantum corrections to the Newtonian potential, the classical gravitational potential of a free particle. floating around in flat space. And what you get is a result like this. So get the classical result minus GM over R, one that we all know from the textbook. And then there are quantum corrections, one loop. So they're proportional to the Planck length over the distance to your particle. And they come with some coefficient that depends on the number of matter fields that are fluctuating around in your vacuum. And well, okay, I've given you Planck lengths. So ns, number of particles of spin s. And then if you have the standard model, you can compute this number. There are various methods for the calculation. An easy one for all the students is using effective actions, if you are interested. And if not, the result is well established. But what is the problem if you want today, if they go to higher loops or do some graviton corrections? Well, you all know that GR is invariant, or the theory that this diffeomorphism invariant. That means we look at some coordinate transformations of our background metric, x going to x tilde. And well, for simplicity, let's take them infinitesimal, so very small. And then for any field, be it classical or quantum, some field A, we get a transformation, a gauge transformation, which is given by the Lie derivative with respect to that field xi. Okay, nothing to worry about, let's say, but well, in the gauge theory, we know something observable should not depend on the gauge. Yeah? So we want something that is invariant under this transformation. And well, okay, say if you have the quantity on your background A0, which vanishes, then of course at linear order, this is 0. So very nice, we have an observable, something that we can see and measure at linear order. But the problem is that at higher orders, it becomes gauge dependent because, well, if you want to have something trivial at first order, it will not be 0. So then at second order, whatever you get will be gauge dependent, depend on the coordinates that you choose to parameterize your spacetime. And that shouldn't be the case. But we are, Einstein told us coordinates shouldn't matter. And in fact, you can turn this again around. If the variation vanishes at some order, then the order before must be a linear combination of Kronecker deltas for the indices, if you have a tensor, with some constant coefficients. And this is also well known. It's called the Stuart-Walker lemma. And in particularly, if you look at your metric perturbation H, and you look at these perturbative diffeomorphisms, so you make psi small, yeah, multiply by the Planck length or so, then what you get is, of course, the well-known transformation of a spin-2 field. So it's just a symmetrized covariant derivative of your gauge parameter. And then what you can do, what people have done to solve the problem, is you decompose your H into 2 parts. Namely, one is, well, which are called invariant part, H inf, which doesn't transform at all, and the Lie derivative of your background metric with some field Z, which transforms in such a way, well, that it gives exactly your gauge parameter. And this can be done in a variety of ways. One can think of many ways to make this decomposition. Usually it's non-local. So it will involve some, say, inverses of a Laplacian, which is a non-local, the Green's function, 1 over R. And for example, a well-known example are Pardini variables, which are known in cosmology and used. And then if you think about what is the Newtonian potential actually, well, you go back to your GR textbook and it tells you, well, it's 1/2 of the time component of your metric, perturbation, because we look at the metric perturbed by a particle. And in particular, it should be, of course, it's something measurable. So it's the expectation value of the invariant part. Okay. So far, so good. Everyone with me? Not yet sleeping? Very good. What can we do at higher orders? Yeah, at linear order, everything sort of works. It's nice. At higher orders, well, we have to think about what we do. And to solve the problem is something that has been solved, again, by many people over a long time. One looks at so-called relational observable. So that means thinking about how you actually measure something. You do it by having an instrument, a device, a telescope, whatever, a material thing. Then you look at other matter stuff coming into that. So practically, what does it mean? We have 4 fields x mu, which determine our position in space. For example, the corner of the table here. So that depends on the matter fields that make up the table. Yeah, that depends on the fields of my theory, and they are in general dynamically. And what you want is that these transform as scalars under diffeomorphisms. Coordinate scalars should be scalars. Very nice. They have some background value. And then we do perturbation theory. We look at perturbative quantum gravity. So we expand background, first order, second order, and so on. And you invert that series, which you can perturbatively. And then you get something that transforms under diffeomorphisms inversely to a scalar. So you just inverted the series that gives you a scalar. And then the invariant observable, which I call here curly A of chi. How do you obtain this? You take your field A, can be anything that you want to measure. You evaluate it at the position x0 mu, but holding the capital X, so the full theory is fixed. Okay, what's the interpretation of that? It's relational because it relates A to your coordinates, to whatever fields make up these coordinates. So the x mu, they are called configuration dependent coordinates, depend on your field configuration. And A of chi is the value of your field that you want to measure, your field A, at the point where the chi is equal to some coordinate x. And then this is the field on your background space-time by valuing it at x0. And then one can check that this construction gives something invariant for A. So this doesn't transform under diffeomorphism, which is very nice because then we can observe it. Gauge theory, standard law. The question is now just how do we get these scalars? How we can get these x mu? If we're on very generic space-time, highly fluctuating, whatever, we can just use some curvature scalars. Riemann squared, Ricci squared, covariant derivatives, whatever you fancy today or tomorrow. And this has been done by people already in the 60s, 70s. If you're not on a generic space-time, if you're saying flat space-time or inflation, we're just put the talk right now, you don't have so many independent curvature scalars. In flat space-time, everything is 0, so it doesn't work. What you can do is you can add scalar fields by hand. So just for scalar fields, the very known example or model is the so-called Braun-Kuchar-Dust. So you add 4 dust fields. But of course, the problem is if you add something to your theory, it changes the dynamics. So also the dynamics of the field that you want to measure are changed by this addition. And this is very nicely shown in this paper, quite recent actually. So then the question is, well, can we do better than this? Of course, we're here in the talk, so the answer is yes, we can. Okay, cosmology, this is what I just told you. In cosmology, we have one scalar field, basically the inflaton, and that's it. And so the first complete solution to this problem in the cosmological context was given, well, by now 6 years ago, by a paper with very many people, but just put et al. And the idea is that you look at your inflationary space-time, you have some time and spatial hypersurfaces, and on the background, the spatial coordinates are harmonic. Laplacian of x is 0, trivially. Second derivative. So what can you do? For time coordinate, you take your inflaton field. That's nice. But for the spatial coordinates, you define them as harmonic coordinates for the full Laplacian. So you generalize this equation to your perturbed geometry. Take hypersurfaces of constant inflaton field. These are your spatial slices. On those, there is an induced Laplacian. And then you define xi as solution to the equation full Laplacian xi equals 0. And solve that order by order perturbation theory. Works to all orders. Works very nicely. You can generalize that idea to flat space, to something which I call causal harmonic coordinates, because the Laplacian, of course, is non-causal. Yeah, that's influence from space-like separations. Maybe you don't want that. You can also use something that the cosmologists call geodesic light cone coordinates, which is very close to observations. Basically, you think about how a telescope measures information, well, by light signals. So we should look at something. And this, for example, as well, we have in this paper, and there are many references in that paper if you're interested. And then you compute the observables in these coordinates. Okay. A nice example are, well, so-called invariant metric perturbation. So you take your metric, you take the coordinates that you have, invert the series, plug it in, and then you need to multiply by Jacobian as usual. And you subtract the background metric, flat space-time. And this is something that now doesn't transform under diffeomorphisms, perturbatively to all orders. And if you look at what comes out, well, first order expression is nice. So to first order, you just get your original metric perturbation, and then you have a term that corrects. So there's a correction, which basically, well, I told you, the x are constructed such that they transform as a gauge parameter. So if you make a gauge transformation of that, you get the symmetrized derivative of xi. And here this transforms as xi, so this just gets subtracted and you get something invariant. Yeah, this works to all orders. It's wonderful. It's a very nice construction. And one can use this to compute things. It's not that complicated. Well, I've done some works. For example, you can now look at graviton corrections to the Newton potential, which are otherwise gauge dependent. But of course, if you have a gauge invariant observable, they are gauge invariant. You can use compute corrections with the Hubble rate and inflation. Many people have done that in many different approaches, but not all have paid enough attention to gauge invariance. So well, one can do things. And then, well, last question. I think I'm well on time, so I can maybe slow down a bit. Now, these coordinates, these x, they are non-commutative. Why? Okay. First, I want to show you another example in flat space. Let's do this. So in flat space, we have generalized harmonic coordinates. Yeah, just some simple example. And then to first order, as I said, one can compute this to all orders. At first order, what you get is you get the integral of some metric perturbation, some combination. That comes from the expansion of the D'Alembert here. First order, basically. And then you integrate that with the Green's function of the D'Alembert of the background space. So Green's function that solves d squared g equal to delta. Which Green's function you take, that's part of the specification of your coordinates, your system. In the classical theory, you would think, well, you take a retarded Green's function. Of course, things should evolve in time, so it should be retarded. And in the quantum theory, maybe you want to use the Feynman propagator. One needs to specify this. It's part of what defines your coordinates and does your observables. And now you see, well, of course, the h, if you quantize them, have a non-trivial commutator. So obviously, the x's also will have a non-trivial commutator. So just by thinking about how you actually measure things in gravity, how you actually can construct observables there, automatically non-commutative coordinates drop out, which is, I think, a very nice thing. Okay, and then let's give some details on the computation. There are a lot of students here, might need to do computations. It's a linear theory, yeah, at first order, very linear. So the commutator is, of course, proportional to the identity, and then you take the expectation value. Use the standard graviton propagator and the Donner gauge. The Donner gauge is nice because it's very simple, the tensor structure. The computations become simple, and GF is the usual scalar Feynman propagator. So, and then you give a student and tell him compute, and then the student will come back and tell you, well, that's all infinite. Something doesn't work. What is the problem? The problem is, of course, this one here, the propagator, and also therefore the graviton propagator, only decays like a power of the distance. So if you integrate that over all space-time, not once, but twice, you get something that diverges at infinity. So some infrared problems. Then, well, you think a bit and you read a bit of the literature, and then you see, well, there are related things. So there are papers by people from York, Higuchi and collaborators, who have thought about things in the zeta space, and they find not these coordinates, but some related things, and they find very similar divergences. And the solution is not to use the Feynman propagator, as you naively would. Because in that case, what you get here is not an expectation value, but an in-out matrix element. So instead, you have to use the in-in formalism, also known as Springer-Keldysh or closed time path and so on, which computes true expectation values. And then what you do is, well, you do not integrate only forward in time, but you add a backward part. It's simple as that. Duplicate your fields. This is also well known to practitioners in cosmology. They use that all the time. If all the fields live on your forward contour, you get time-ordered things. All live on the backward contour, you get anti-time ordered things. If they are mixed, you get Weidmann functions. So you can compute expectation values, which are Weidmann functions. And of course, this also applies to the coordinates. So you get the plus coordinate living on one branch and the minus living on the other. And basically what you do is you sum over everything. And for the backwards part, you add a minus. Now you can give it to the student again. And tell him, well, look, you use this. And the classic limit, everything is fine. You get a retarded propagator as you want. And the IR divergence is avoided by choosing an adiabatic vacuum at the initial time. And this is also known, very well known. It's in textbooks, Peskin and Schröder, somewhere in the beginning, part that everyone always skips over. So what you do is you slightly tilt your time contour into the complex plane, integrate, and then take the limit epsilon to 0. And then you get this result. It's advisable to do this in Fourier space. So this is the Fourier space result. Doesn't look very nice, maybe, but the coordinate space result is very remarkable. So it's very different from any other commutation relation I've seen written down for coordinates. Because, well, it's a fully Lorentz invariant result in flat space. say the Doppler Fredenhagen-Roberts proposal with a constant anti-commutator that's not Lorentz invariant, except in 2 dimensions. This one is fully Lorentz invariant. It vanishes for space-like separations, so it also fulfills micro-causality. Interesting. And for time-like separations, well, it depends on which one comes earlier or later, and then it's a constant. So it's I think, yeah, it's completely different from everything I've seen so far, but it just drops out of the theory. There's really nothing you have to put in. Okay, and one moment. That was the first order correction. So for the full coordinates, well, the background coordinates obviously commute. So write down the expansion. Here the Planck length appears. That's Planck length is square root of the Newton's constant in that case. And then you get this. Yeah, it's basically the same as I had written down before. Just now it's the Planck length appears. And just to compare with what is known before, well, the most general form that you can write down is, of course, something like this. Yeah, with some theta mu nu that depends on x and y. And say, and of course, it must be antisymmetric. So if you interchange both indices and both fields, you get a minus sign. But this you can do in 2 ways. Either Doppler Fredenhagen-Roberts, it's constant, then it must get a minus sign just from switching the indices. Or in our case, this is the symmetric matrix. Of course, it's just the metric. And the antisymmetry comes from the sign function that appears there. So this depends on x and y. And so it's the second possibility. And well, you can also now use plug in standard deviation formula, yeah, for operators. And what you get is, well, something which I have called, or we have called, the generalized uncertainty principle. People might object to that. So what you see is that measurements of coordinates with time-like separation, yeah, so when this one is 1, Heaviside theta function, they are uncertain. So if you measure again and again and again, and it's time-like separation, you get something that can be uncertain. It fluctuates a bit, and the standard deviation is exactly the Planck length. And also that falls out of the theory. I haven't put that in by hand. I haven't put in any scale by hand yet. This is really, this Planck length is the one in front of the Einstein-Hilbert action, the 1 over G Newton. That's nothing else. And measurements for space-like separations, they can be exact. So micro-causality is fulfilled. Okay, that's it. Thank you very much. Conclusions, yeah, you can read them, I think. And in future work, of course, I want to do more. I want to do higher orders and Planck lengths, different backgrounds, maybe connect with observation. And I, of course, I haven't done this alone. There's Albert Much here, my collaborator, sitting down the back over there. You can also, ask questions. And Kyriakos Papadopoulos, who unfortunately couldn't come, but sends his greetings to all of you. Thank you very much.
Okay, since we can ask questions, are there some? Yes, Fedele?
The Lorentz invariance still holds at higher higher terms in the expansion. Is there a reason for? I mean, can you already say without calculating that will be Lorentz invariant?
Yes, so I think Lorentz invariance will be preserved at all orders. I haven't computed it, but that's what I expect, because it's standard quantum field theory, just they repackaged in an unusual way. So Lorentz invariance should hold to all orders in Minkowski.
May I also ask something?
Yes.
Yes, but time reversal is not a symmetry of this commutative relation, seems, no? Because, or not?
Time that changes the sign, yes.
Yeah. So, have you in mind any interpretation for that?
No, sorry. I don't. If you have any, I would be happy to hear it.
Okay.
My question is in this slide particularly, as I saw previously, what you did was having some kind of at 0 order some commutative coordinates. At the higher orders, you get some non-commutation relations. But going here, it looks like you have some functions on the non-commutative coordinates. You are interpreting this expression like functional analysis or something like that?
Very good question. No. So since this is multiplied by Planck length squared, and I'm dropping terms of order Planck length cubed, these are just the commutative background coordinates. So the idea would be to check if this relation also holds for the full non-commutative coordinates at higher orders, or if there are other corrections. So this is why I've written it in this suggested form. But at that order, these are commutative.
It looks like you could, for example, have some expression that has some formal power series or something like that.
Yes. Yeah. So this is all in the sense of formal power series in the Planck length. It's all perturbative. Yeah.
Thank you.
Question here.
I just want to understand, is it correct to say that this non-commutative coordinates are actually produced from the just coordinates on the manifold by adding, by dressing them, so to say, with gravitational degrees of freedom, so as to make them gauge invariants like Bardeen variables? So they are kind of a Bardeen variables for coordinates, right?
Yes. That's completely right. Like in QED, to describe the electron fully, you also need to address it with a photon cloud. But here we need to address this with gravitons.
Yeah. Yes. But I understand that this Lorentz invariance is actually something that comes with no price, really, because the whole procedure is manifestly Lorentz invariant to start with.
Yes, completely correct. Yes.
Okay, thank you.
So I just would like to understand better your expression. When x is equal to y, so when you use the same coordinate, what is it?
Yeah, so if x is equal to y, it depends on which direction you approach from. If you approach from space-like separations, you get 0. If you approach from time-like separations, you get plus minus constant. So, I mean, this is a distributional result in a certain sense. Yeah, this is a distribution, or if you want, it's a discontinuous function. So you can't really set x equal to y. You can take limits, but these limits depend on which direction you come from.
Because you see, I'm used to think of a non-commutative space as given by some generators and relations, some of which are brackets.
Yes.
So here I should think in a completely different way.
Yes. I mean, of course, where it comes from is that you take your first order correction, evaluate at 2 different points. And if you put them here, if you would say in this formula, put here the same point, you will get the integral of, 0. So if you start from here, at least naively, you would get 0. But, you can't really exchange the limit with the integral, of course. Yeah, mathematically. So it really depends on which direction you come from.
Thank you.
So it's completely, it's different.
Thanks.
Yeah, I do not see any hand raised, so we thank Markus Froeb. And the session is closed until tomorrow.